Okay, for this question it says, for what values of x does f obtain a relative minimum? What are the relative minima? Select the correct answer choice below, and if necessary, fill in the answer to complete your choice. So what we're looking for in this example is a relative minimum. A minimum, the word minimum, is describing the y. And so what we're looking for is a small y value, or the smallest y value. Now that's with a slight caveat because we have the word relative. And the word relative added to the minimum means that we want to be able to look in a localized area relative to nearby the point we're looking at. And it doesn't have to be the smallest y value on the whole picture, it just has to be the smallest y value in the nearby area. So for this example, this picture that we're looking at here, we can see right here is a dip in the graph. And if we zoomed in on that place, we could see that this point right here, which is labeled as -4, -5, would be the smallest, that point has the smallest y value in that nearby area. And so we're going to say that -5 is the minimum, and it occurs at the x value of -4. And that's the only dip in this graph. And so this is the only relative minimum. So there's only going to be one relative minimum. The minimum value is -5, and it occurs at x equals -4. In the next part of this question, it says, for what values of x does f obtain a relative maximum? What are the relative maxima? And select the correct choices below. If necessary, fill in the answer boxes to complete your choices. So for finding a relative maximum, this word maximum is describing y. So we're looking for a highest y value. Just modify that just a little bit with the word relative. That means that we want to be able to zoom in on a particular area, and that would have the highest y value in that area. So looking at the picture that we have here, I can see two places on the graph that achieve a peak. And if we were to zoom in on those two areas, I can see that those points would obtain a maximum in that area, the highest y value in that area. So for this one here, we would have a maximum of 2. That's a max y value of 2 at x equals 5. And for this one here, we have a max y value of -8. Not -8. A max y value of 3 at x equals -8. So these would be our relative maximums for this particular graph. Now notice that we do have one being higher than the other. So this max of 3 is higher than this max of 2. But that word as a part of the vocabulary relative is what allows this graph to have more than one. So that word relative says you're going to zoom in and only look at that isolated area, and for that isolated area we do have a maximum of 2. So once again, we're not looking for the maximum on the whole graph, we're looking to see if there are any little localized maximums. So there are 2 for this one. So we would select this answer choice here, saying that there are two relative maximum. The leftmost, meaning we're talking about this one first, has a maximum value of 3, which occurs at -8. Then the rightmost, we're now talking about this one, has a maximum value of 2, which occurs at 5. Okay, so this question is determine visually whether the function is even, odd, or neither even nor odd. So what we have to remember with this is that an even function will have y-axis symmetry. An odd function will have origin symmetry. And y-axis symmetry is when we would take a mirror image going over the y-axis, and we would have the two sides of the graph matching up over that y-axis. And then origin symmetry is when you have a mirror image going over the origin, which is 0, 0. And so you're going to have in these opposite quadrants a mirror image. So in those two quadrants and also in these two quadrants. So what I want to do is I want to look at the graph that I have and imagine these types of symmetry to see if I have either one of them. So I'm going to start with the y-axis symmetry. So this is the y-axis, and I'm looking on either side of that y-axis to see if I have a mirror image. And what I'm seeing is that this piece of the graph, if I were to mirror it over the axis, would look like this, and that doesn't match the other side. So this function does not have y-axis symmetry. So then what I want to do is look at origin symmetry. So origin symmetry is when you have in opposite quadrants. So I'm going to focus in on quadrant 1, and then the opposite quadrant is quadrant 3 over here. So this is 1 and this is 3. And I'm trying to see if there's a mirror image. And this one can be a little bit harder to imagine. So I'll take you through a way that you can imagine it. So what you can do is, I'm going to start with this piece of the graph right here, and I'm going to imagine reflecting it over the x-axis, and then imagine reflecting it over the y-axis. So this is like 2 over here, so when I reflect it, it would be 2 over here. So that piece that I originally talked about reflected once over the x, and then when we reflected over the y, landed right on top of this piece over here. And so it is matching for origin symmetry. And let me try to do it with this piece right here as well. So if I'm starting off with this piece right here, which is in quadrant 2, and I reflect over the x-axis and then reflect over the y-axis, I'm landing right on top of that graph in the 4th quadrant. And so this graph does have origin symmetry. And functions that have origin symmetry we would categorize as odd. So this is an odd function. This question says determine if the function is even, odd, or neither. And our function is g of x equals square root of 4 minus x to the 6th. So when we're determining if a function is even or odd, we should know the definition. The definition of even will be if f of negative x is equal to f of x. And these are some symbols that represent y-axis symmetry. And so what that means is you would have a mirror image going over the y-axis. When a function is odd, it would satisfy the definition f of negative x is equal to negative f of x. And this is a symbolic way of representing origin symmetry. When you have origin symmetry, that's when you're symmetric in opposite quadrants and you have that mirror image going over the origin. So for us to figure out if this function is even or odd, I'm going to do a calculation, and you'll notice in both definitions we use f of negative x as a part of the definition. So I'm going to do the calculation g of negative x so that I can compare whether our function matches this definition, which is when f of negative x equals f of x, or if it matches this definition where f of negative x is negative f of x. I like to think of these as the same and the opposite. So the first one, which is even, equals, the two y values equal each other, and you can see that the y values are the same here for these points. And opposite, we've got a negative here, and these y values are opposite of each other when we have origin symmetry. So I'll do the calculation g of negative x. Everywhere I see an x, I'm going to change it to negative x. And negative x to the 6th power, that's an even number of negatives, and those negatives will cancel out. And so you can see my calculation of g of negative x is equal to the original or the same as the original. And so this is fitting with the definition of an even function. This function is even, and if we were to graph this, the graph would have y-axis symmetry. So on this question, we have a picture of a graph, and it's labeled right here. The graph is labeled as a function, y equals f of x. And we have two questions related to this picture. The first one says, for how many values of x is f of x equal to negative 5? So let's think about what these symbols mean for a second. We have to remember that f of x is the same thing as y. So this is saying y equals negative 5. For how many values of x is y equal 5? So one way we can think about this is to draw a horizontal line. Y equals negative 5 is a horizontal line. And that horizontal line will be at y equals negative 5. I'm going to draw it right here. And this horizontal line, if we think about it, every ordered pair on this line will have the y-coordinate being negative 5. So every ordered pair. Now we're interested in only the ordered pairs that are on the graph. And so we only have this one ordered pair that's on the graph that has a y-coordinate of negative 5. And so we can say there is one x value in which f of that x value is negative 5. F of 2 equals negative 5. Then the second part says, what is the value of f of 6? F of 6, when we look at these symbols, what we should realize is that the number in the parentheses is the value of x. So we know that x equals 6. and f of 6 is referring to the y. So I'm going to draw this time a vertical line at x equals 6. So 1, 2, 3, 4, 5, 6. Here's 6. I'm going to draw a vertical line at 6. And this vertical line represents all of the ordered pairs that have an x-coordinate of 6. But we're really only interested in the ones on the graph in f of 6. So we only have one that's on the graph here. That ordered pair is 6, negative 1. So that tells us that f of 6 is negative 1. The y, and I for whatever reason wrote negative 5 and said negative 1. So the y is negative 1 when x is 6. For this question, we want to sketch the graph of the following function and identify all properties that apply. We're going to start with sketching the graph, and then we'll take a look at those properties. So to sketch the graph, I'm going to make a chart, a table of x's and y's. And I like to choose a standard set of x's, negative 2, negative 1, 0, 1, and 2. And substitute those into the function to get the y's. So if I substitute in a negative 2, that would be negative 2 squared is positive 4. Negative 1 squared is positive 1. 0 squared is 1. 1 squared is 1. Let me back up because 0 squared is not 1. 0 squared is 0. 2 squared is 4. And this gives me a set of ordered pairs that I can plot to kind of sketch my graph out of. So we have negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. I'll plot these points on my graph. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. And what I see as a pattern is a U-shaped graph. This graph is called the parabola. And it looks like this. So there's a sketch of the graph. And now I want to go through these properties to see if they apply. The first property says this function is an odd function. An odd function has origin symmetry. So a graph or a function that has origin symmetry will have a mirror image going over the origin. So that means that your picture in the first quadrant would be a mirror image in the third quadrant. And if you have a picture in the fourth quadrant, it would be a mirror image in the second quadrant. And you can clearly see in our picture that our third quadrant right here, this is quadrant 3, is completely empty, and yet we have points in the first quadrant, so this function cannot be an odd function because we don't have a mirror image in these opposite quadrants. So we would not check that first statement. The next statement says the function is a linear function. A linear function happens when you have your variable to the first power. Our variable is squared, so this is not a linear function. Let's see the next statement. So the next statement says the function is increasing on the interval from negative infinity to infinity. As I look at this graph, starting from left to right, My y values are decreasing along this section and increasing along this section. So my function is not increasing from negative infinity to infinity. It's decreasing along this section on the left, which is from negative infinity to 0, and it's increasing on the section on the right, which is from 0 to infinity. So this statement does not apply. The next statement says the function is an even function. An even function is a function that has y-axis symmetry. So when a graph has y-axis symmetry, you would have a mirror image folding along the y-axis, meaning that everything that you have on the right, you have a mirror or reflection on the left of the y-axis. The graph that we have here, if we draw a line along the y-axis, you can see that you have a mirror image on the left and right of that y-axis. So we would check this property to be true. The next property says the domain of f is negative infinity to infinity. I'm going to take my ruler and hold it vertically and think about when is the first time my ruler would hit the graph. Because of this line going on forever, it's going further and further left the higher and higher we see it. The domain would start at negative infinity, and because of this line it's going further and further right, the domain would stop at infinity. So my domain on this example would go from negative infinity to infinity, and so this property is true. I would keep that one. The next property says the range is negative infinity to infinity, so I'm going to hold my ruler horizontally and go from bottom to top. The first time I hit the graph wouldn't be until I get to a y value of 0. So for this function, the range starts at 0 and continues on to infinity. And so I would not select this property. The final one says none of these properties apply. Since I've selected 2 of them, I wouldn't check this one either. So the 2 properties I would select is that this function is an even function and the domain is from negative infinity to infinity. Thank you for checking out my videos. Have a great day.